Once upon a time, in the world of theoretical physics, there was a deep mystery lurking at the intersection of two of the most fascinating phenomena in the universe: quantum entanglement and black holes. These two concepts, each extraordinary in its own right, seem to be governed by very different rules. Yet the deeper scientists dug, the more they realized that these two mysteries might be connected in surprising ways. So, quantum mechanics, the branch of physics that governs the behavior of the smallest particles, like electrons and photons, revealed an oddity called quantum entanglement. In this strange phenomenon, particles that were once part of the same system could become entangled in such a way that the state of one particle was instantly linked to the state of another, no matter how far apart they were. Like this spooked even the greatest minds, including Albert Einstein, who famously called it spooky action at a distance. Entanglement defied the classical idea of locality, the principle that objects can only be influenced by their immediate surroundings. But despite this, experiments confirmed its reality, and quantum entanglement became central to many cutting-edge technologies, such as quantum computing and cryptography. Meanwhile, in the world of cosmology, black holes, regions of space-time with gravitational forces so strong that nothing, not even light, could escape, posed another puzzle. According to Einstein's theory of general relativity, black holes were believed to be regions where gravity was so intense that it warped space-time itself, effectively trapping anything that crossed their event horizon. But something strange happened when physicists tried to combine quantum mechanics with general relativity. In the 1970s, Stephen Hawking discovered that black holes actually emit radiation, now known as Hawking radiation. This meant that black holes could slowly evaporate over time, and the idea of black holes as permanent objects began to unravel. Here was the paradox. Hawking's radiation suggested that information falling into a black hole could eventually be lost, leading to what's known as the information loss paradox. According to quantum mechanics, information cannot be destroyed, but if a black hole evaporates completely, what happens to the information it swallowed? This posed a serious challenge to the foundation of quantum theory. As these two puzzles lingered, a breakthrough emerged that began to connect quantum entanglement and black holes. In the 1990s, physicist Juan Maldacena proposed a radical idea known as the holographic principle. This principle suggested that the entire universe, or at least the information within a black hole, could be encoded on a lower dimensional surface like a hologram. But the twist was that this surface could be described by quantum mechanics, while the bulk of the black hole's mass and gravity could still be explained by general relativity. Further, researchers started to think about entanglement in the context of black holes. A landmark paper in 2007 by Mark van Raamsdonk showed that quantum entanglement might hold the key to understanding black holes. According to this work, the geometry of space-time around a black hole could be described by quantum entanglement between particles in its interior, and those outside. The deeper you look into the black hole, the more entangled the particles within it become with the particles outside. This connection led to a bold hypothesis, the firewall hypothesis. The idea was that when you fall into a black hole, the quantum entanglement that connects you with the outside universe could be destroyed, creating a firewall of high energy that incinerates anything attempting to pass through the event horizon. This was an unsettling idea because it contradicted previous theories that you could cross the event horizon without noticing anything unusual. Yet it provided a potential way to resolve the information loss paradox, suggesting that the entanglement between the particles inside and outside the black hole could ultimately preserve the information even if the black hole evaporated. As physicists continue to study the relationship between quantum mechanics and gravity, the idea of quantum gravity is emerging. Theory that aims to unify quantum mechanics and general relativity. One of the key goals of quantum gravity is to explain how information, including that inside black holes, is preserved without violating the fundamental principles of either theory. Entanglement could hold the key to resolving this ultimate question. Some theorists propose that black holes themselves could be quantum entangled with other distant objects or even with other black holes, a concept referred to as quantum correlations. In this view, the information swallowed by black holes may not be lost, but could be spread out across the universe, encoded in the very fabric of space-time itself. Some even think that black holes may act as cosmic quantum computers, processing and storing vast amounts of information in a way that we are only beginning to understand. Just as quantum entanglement allows for instantaneous correlations between particles, black holes may create a kind of vast entangled network linking distant parts of the universe in ways we are still unraveling. In the end, the relationship between quantum entanglement and black holes could represent the frontier of theoretical physics. By understanding how entanglement operates near black holes, scientists hope to unlock the mysteries of the universe, revealing how gravity, quantum mechanics, and information theory can all work together in a unified framework. Perhaps one day, as we peer deeper into the black holes and probe the quantum fabric of space-time, we will uncover the fundamental truths about reality, where the smallest quantum particles and the most massive objects in the universe are not as separate as they seem, but rather part of a grand, interconnected whole. And that, in a nutshell, is the ongoing scientific story of how quantum entanglement and black holes might be related. It is a tale still being written, one that could change our understanding of the universe forever. Please remember to like and subscribe, and feel free to leave any content suggestions in the comments section.